Hello everyone, so in this video I'm going to talk to you about second order differential equations. Now this is a simple video, just basically showing you some examples of how to solve them. I don't offer proofs as to why the method works. So if you're tuned in just to see a set method for solving, then you've tuned into the right video. If you want a proof of why this method works, you've got to look somewhere else. Okay, so this is what we call a second order homogeneous differential equation. Called second order because it's got a second derivative. First derivative and then of course just y, but the highest derivative is 2, so it's called a second order differential equation, and it's homogeneous because basically this one is a simple one, it's equal to 0. Homogeneous means something far more complex and complicated. If you'll look it up, I suggest you do so. I don't have the time to discuss homogeneous equations right now, but this is the sort we'll be looking for. Now this is a quadratic, okay, it's quadratic in style because you've got something squared plus essentially a linear term plus this. And so to make the equation simpler to deal with initially, we're just going to write down what that quadratic looks like, but without the derivative terms. So you've got a d to y dx squared, so we'll write as am squared plus b dy dx plus bm plus c equals 0. Because to begin with, we've got to find the roots of this quadratic. Okay? This quadratic here is what's called the auxiliary equation. This is a term that you need to be aware of. You need to know it's called the auxiliary equation, and we tend to use m because y and x have already been taken, haven't they? And the first thing is we've got to solve this. Now there's 4 separate possibilities for this. Okay, either you're going to get 2 distinct real roots, okay, to this quadratic, or you're going to get 2 roots that are repeated, okay, so the same, or you're going to get purely imaginary roots, or you're going to get complex roots, and those will be complex conjugate, of course. Now, depending on which one you get, your solution to the differential equation is going to be determined by this. So for this case, when you've got 2 real distinct roots, alpha, beta, your solution looks like this. Y equals a e to the alpha x plus b e to the beta x. As I said, this video is not a proof of why this works. This video is the rules that you need to be able to use to solve these differential equations. Okay? I might have another video somewhere demonstrating why these work, okay, but not yet because this is the first one I'm recording. If you've got this situation here where you've got real roots that are repeated, you need to have this as your general solution. Y equals, and then a plus bx e to the alpha x. So notice the roots, the alpha goes here, or if you've got distinct roots here and here, the a and b, the capital A and B, those are constant values. Those are constants that remain part of your general solution. And then in this case here, we've got 2 imaginary roots, and I've used the Greek letter omega for this. So either it's positive or negative, some number times I, like 5i or something. And I've used that letter omega to represent that value. The general solution looks like this. So a cos omega x plus b sine omega x. Okay? Again, the a and b, those are constants that remain. The omega is the value you've got here from your imaginary roots. Finally, the complex roots case, it looks like this. So notice it's actually the same as the pure imaginary case, okay, except I've used q instead of omega. But when it's complex conjugates, you've obviously got a real part and an imaginary part. The real bit then is the exponential form. So you have e to the, and that's a p, x, so whatever the real component was, and then in brackets, basically this for the imaginary. A cos qx plus b sine qx. Okay. So those are your general rules. Right, let's do some examples now. So I'm going to do one example for each one. Right, so this one here, okay, this one, first step, set up the auxiliary equation. Okay, if you're doing an exam, like an A-level exam, the examiners want to see that. Okay, they want to see your auxiliary equation. And then you solve that auxiliary equation using the standard method of solving a quadratic. This one factorizes, and notice you've got real distinct roots. So it's going to follow this case here. So these roots, m is negative 3 over 2, or m equals negative 1, they're going to feature here for your general solution. So for your general solution, you're going to have y equals a e to the, and then first root, negative 3 over 2x, plus b e to the second root, negative x. Okay. My advice is you just put these in numerical order. There's no particular reason, it's just that I've noticed most mark schemes tend to favour having these in alphabetical order. Okay. So if you want to match the mark scheme perfectly, just go for numerical order, okay? And that's it. That's what we call a general solution. For a particular solution, you'll be given some initial conditions that you substitute in to work out what A and B are, but that's not what this video is about. This video is just about finding a general solution. Okay, so that's your first case. I'm just going to see if occasionally I'll do that in case you want to take a screenshot, obviously without me in the picture. But if you want me in the picture, then I'll just pose for you. There you go. So let's go for the next one. So this is a second case. So same situation, always set up an auxiliary equation first. So that is going to be m squared minus 6m plus 9 equals 0. Okay. Then you solve that auxiliary equation. Notice the repeated roots that you'll have, because you'll have m equals 3 twice, m minus 3 squared. And in this particular case, the repeated root, you just follow this rule here. So you've got a plus bx and then e to the, and then whatever the root is, 3x. Okay, and that's your general solution. I'm hoping you find these easy. They are. Trust me, if you just remember these rules, then you're set. You're good to go. Okay? The challenge, of course, is remembering which one is which when you're actually doing this under examination conditions. So that's your second example. They are moved away for a screenshot in case you wanted to. Next one, okay, so I'm going for the imaginary roots here, the purely imaginary roots. So notice in these cases with the purely imaginary roots, there's no dy dx term. Okay, why is that? Because you're just going to end up with m squared and then equals negative something, obviously to get the imaginary roots. So in this case, you're going to have m is positive or negative 4i. Okay, so they're easily recognisable. You can spot them straight away. These ones, they're going to be the imaginary ones. Okay, so in this case, the omega is the 4. Okay, so you're just going to have your general solution as y equals a cos and then 4x plus b sine 4x. Okay, that's it. Yeah, I hope you find it is easy because, as I said, once you get past the rules that are needed, it is pretty straightforward. Okay, I find these easier than first order differential equations. Next, last case. So this one, you set up your auxiliary equation first of all. Okay, I'll keep writing this down because it's a term that's got to stick. You've got to know the term auxiliary equation. You solve the auxiliary equation and you're going to get this. Okay, so complex roots, obviously conjugate 3 plus 5i, 3 minus 5i. And then for this case, you just need to follow this set pattern. So remember the real component there will be e to the 3x, because that's the real component. And then for the imaginary component, the 5, you've got a cos and then 5x, b sine 5x there. Okay. So that is it. Right. I'm hoping that was useful to you. Okay. If this is your first go at second order differential equations, maybe just watch that again. If this is just a recap, well, I'm hoping it made sense to you. Okay. Thanks for watching. I'll see you again.